Graphs of polynomial functions. A function is odd if f of negative x equals negative f of x for all x in the domain of the function f. This property has a graphical consequence shown to the left. Notice that the point 1, negative 2 here rotates to the point negative 1, 2. Those polynomials that are odd functions display rotational symmetry about the origin. If a function is odd and a, b is on the graph, so is negative a, negative b. A function is even if f of negative x equals f of x for all x in the domain of the function f. This property has a graphical consequence shown to the left. Notice that the point negative 1, negative 3 is reflected across the y-axis to the point 1, negative 3. Those polynomials that are even functions display symmetry across the y-axis. If a function is even and a, b is on the graph, so is negative a, b. For a polynomial function to be odd, all of its exponents must be odd. For a polynomial function to be even, all of its exponents must be even. Here are some odd polynomials. X to the 7th plus 2x cubed, so we have odd exponent, 2x to the 5th minus 5x to the 1st, 5 is odd and 1 is odd. And here we have x to the 1st minus x cubed, 1 and 3 are both odd. Here we have x squared minus 4. You can imagine 4 being multiplied by x to the 0 power, which is 1. 2 and 0 are both even. Here we have 3x to the 4th. This 4 is even, minus 11x squared, this 2 is even. And here we have 3x to the 8 minus x to the 4th, 8 and 4 are both even. So whenever you have a constant with no variable, that is assumed to be even. So you can't have a constant in an odd polynomial at the end. Neither even nor odd. Here we have x to the 4th plus 2x cubed plus 1. So here we have an even and an odd exponent and a constant. Here we have an even exponent, an odd exponent, and a constant. So these are neither even or odd. Prove that g of x equals x squared minus the absolute value of x plus 8 is even. The function g is even if g of negative x equals g of x for all x in the domain of the function g. To start, find g of negative x. So when we plug negative x into this function, we get negative x squared, which is negative x times negative x, which is positive x squared, minus the absolute value of negative x, and the absolute value of negative x is the absolute value of x, and then plus 8. So what we end up with is exactly what we started with. So the right-hand side should look familiar because it is the original function. G of negative x is g of x for all real numbers, therefore the function is even. A polynomial function is continuous. This means that a complete graph of any polynomial can be drawn without taking the pencil off the paper. There are two important ideas here. The domain of a polynomial function is the set of real numbers, from negative infinity to positive infinity. And the graphical consequence is that there are no breaks in the graph. In particular, there are no vertical asymptotes and no holes. Note, a complete graph is a graph that reveals all of the important features of a function, like turning points, intercepts, and end behavior. Beware! Graphing polynomials with a graphing calculator or with computer graphing software is really helpful, but be careful about recognizing whether or not you are looking at a complete graph. Here's an example to consider that illustrates the issue. This graph right here is a detail of f, not the complete graph. This is the complete graph of f because, as you can see, we've just zoomed in on this portion, but there's another very important feature which is down here, missing from this graph. A zero of a polynomial is an input that gives an output of 0. The number z is a zero of polynomial p if and only if p of z equals 0. A zero is also called a root. These two words are interchangeable. With polynomial functions, real zeros correspond to the real numbers on the x-axis where the graph of the polynomial touches or passes through the axis. Note, a zero is not a point, it's a number. An x-intercept is a point on the graph and has an x and y coordinate. It follows that if a polynomial passes through the point 5, 0, then 5 is a zero of the polynomial. Consider the polynomial p of x. Determine whether the statements are true or false. P of 2 equals 0. When x equals 2, y does equal 0, so this is true. Negative 1, 0 is a real 0 of p. Well, negative 1, 0 is an x-intercept. Negative 1 is a 0 of p. So this is false. However, this one's true. Negative 1 is a 0, but this point is an x-intercept. It would not be called a real 0. Negative 4 is a root of p? Yes. The point negative 4, 0 is an x-intercept, therefore negative 4 is a 0 or a root of p. Finally, 2, 0 is a root of p. This is false. 2 is a root of p. 2, 0 is an x-intercept of p. True, false, true, false, true. An even degree polynomial of degree n has at most n real zeros. Here are some examples of second degree polynomials. Here we have no real zeros. Here we have one real zero. And here we have two real zeros. So a second degree polynomial can have 0, 1, or 2 real zeros. An odd degree polynomial of degree n has at least one real zero and at most n real zeros. Here are some examples of third degree polynomials. Here we have one real zero, here we have two, and here we have three. So a third degree polynomial can have 1, 2, or 3 real zeros.